Good evening, gentlemen. So what I have here is a Unit 3 review video. This will go over everything that we discussed in Unit 3, along with some examples. Now, I did try to provide at least 2 examples for everything, so I will go through one, and then you will have the opportunity to go through one as well. And then I will go through it again, but it gives you a chance to try on your own. In the description of the video, I do have timestamps for all of the sections, along with places to see certain aspects, so you can go there and skip around, but please use this video to prepare for our test on Thursday and Friday. The first thing I'm going to go over is the parts of the atom. The first thing I want to discuss are the parts of the atom. Now, I understand that this is review, but it is important that you understand the way that we reference the parts. So the first one would be my proton. This is always the identity particle, and it's also my positive charge. What I mean by identity is that is my atomic number. So my atomic number equals my number of protons. If you change the number of protons, you will change the element's identity, and this is why we refer to it as our identity particle. Neutrons are the other ones. The protons and neutrons are what you find in the nucleus. Neutrons are a neutral charge, and these have the same mass as a proton. To calculate your mass number, you do your protons plus your neutrons. This makes sense because the mass is located in the nucleus of my atom. You can have a different number of neutrons. If you have a different number of neutrons, these are called isotopes. The last kind of particle that we see is our reactivity particle, and this is our negative charge. These are mobile, they are outside of the nucleus, and these are going to vary. So they can hop out of my atom to join other atoms and make a charged particle. So we call these ions if there's any charged particles or charged atoms. Now, we did talk about how protons and neutrons have the same mass. A quick refresher for you is that protons have a mass of 1 AMU, neutrons have a mass of 1 AMU. These are why they are contributed for our mass and why we can just simply add 1 plus 1 or 9 plus 9. Now, what is important to know is that AMUs are called our atomic mass units. This is not a real mass, it's just that the mass of a proton and a neutron are so small that we just need something to explain their mass. Electrons virtually have no mass. Their mass is 1,840th of a proton, meaning that it takes 1,840 electrons to equal 1 proton. So because you need a large amount of electrons, we can say that the mass of electron is negligible or close to 0. Now, this is it of our review for the atom. Make sure that you read through your unit packet if you need additional information. But make sure that you know that protons and neutrons are our mass number, protons are our atomic number. We can have a varying amount of neutrons. We use this when we have isotopes for our average atomic mass calculations, and our electrons can move, and these will determine the charge of our ions. Now that we had an opportunity to discuss just the parts of the atom, let's go into what shorthand atomic notation is. As a refresher, shorthand atomic notation is when we are using this. So my X here, this will always represent the chemical symbol of my element, and this is my 1 to 2 letters. However, if I were to look at my red number, this will always be my mass number. Quick refresher, mass is equal to protons plus neutrons. So if I give you the neutron number, you're going to look at the atomic number and add those together. If I say mass number, that is the number that you put in the upper corner. Last but not least is our blue number, my Z down here. This is my atomic number, and if you recall, this is also the number of protons. So when you're doing this, if it says atom, that is neutral, so you do not need to include a charge. You just need to include the chemical symbol, the mass number, and the proton number. Now that we've had an opportunity to discuss the shorthand atomic notation, let's do some practice. I'm going to do the one that is on the left side, and then I will give you an opportunity to do the right side. Quick refresher for you. The first thing I need to remember is that I have my element symbol. I then would have my atomic mass number. Right? And that's my protons plus neutrons. And then I will have my proton number in that bottom. Remember, because it's an atom, it is neutral, so I do not have to worry about a charge. The first one is give the atomic shorthand for a calcium atom with 20 neutrons. If you go to your periodic table, you would see that calcium is a Ca. That is going to represent my X, so I put that there. Next, I find out my proton number. My atomic number for calcium is 20. I will put that in the bottom. I give you 20 neutrons. So to calculate my mass, I'm going to add my protons plus my neutrons. Meaning I do 20 plus 20. And I get an answer of 40. This is all I have to do for my atomic shorthand. What I would like you to do now is you are going to do number 2. You are going to give me the atomic shorthand for an oxygen atom with a mass number of 17. Pause the video here, and I will go over it in a moment. My first step is I look at my periodic table, and I'm going to determine what my element shorthand for oxygen is. In this case, it is 0. I look at my atomic number for oxygen, meaning it is 8, so I put that in my lower corner. Notice I give you the mass number, okay? So you do not need to do any math for this part. All you need to do is write the number 17. If you were curious about the number of neutrons, all you would need to do is take your mass. You would take your mass minus your protons. In this case, I would take 17 minus 8, so I'd be left with a number of 9. The only thing I have to do now is I'm going to put a box around it, but that's it. Because it is a neutral atom, right, I do not have to include a charge. That concludes our shorthand atomic notation review. I am now going to move into the ionic shorthand. We are now in the ionic shorthand notation. This is where I'm going to see a variety of charges. Before we get into that, I do think it's important to review our electrostatic attractions. This is extremely important as we move into some questions, but you do need to know how to apply this on the test. Remember that positives and negatives are going to attract together, whereas like, such as 2 positives or 2 negatives, are going to repel. Okay, so just opposites attract, likes repel. Understanding that positives and negatives are going to attract is extremely important for chemistry. As long as you understand this concept, it'll make a lot of sense, and it will make some things a lot easier as we move later down into this semester. So now that we had the opportunity to talk about that, the next part I want to review with you is about ions versus atoms. Atoms are going to always kind of be my middle particle here. This is going to have no charge, and my protons, or my positives, are always going to equal my negative electrons. So if I look at my atomic number, oh goodness. So if I look at my atomic number, that will now be for my number of electrons. Okay. Now, if I move, meaning if I instead lose electrons, so I have more protons than electrons, these are going to result in an overall positive charge. There we go. We call these cations. So if you look at and see a positive charge, you need to understand that you have less electrons. Now, moving on, if I look at my electron gain, I will have an overall negative charge. This means that my electrons are greater than my protons, okay? And we call these anions. So if I have a negative charge, you're going to add whatever that number is to your protons to get your total electrons. So positive is pretty much subtracting the charge in your protons. If you're adding, you gain electrons, you're going to do an addition. All right. Now, when I talk about ionic shorthand, it's going to be similar to my first one, my atomic, where I'm still going to have the chemical symbol, right? I'm going to have my mass number, I'm going to have my proton number, except now I'm including a charge. Now, there's two ways you can write your charge. You can either write it as a positive 1, for example, or a 1 positive, a negative 1, or a 1 negative. What's most important when you do this is you need to make sure that you're drawing the charges in there. I would not accept just a number 1 or a number 2, even if it's implied, well, Mrs. McCaslin, it's a positive number. You have to include that charge so that way I understand, okay, I have more protons or I have more electrons. So why don't we practice what this would look like when I have an ion? Now, just like our previous one, I am going to do the first one with you, and then you will have the opportunity to do the second one. Quick refresher. I have my chemical symbol, I have my mass number, I have my protons, except now I'm including my charges. The first one I'm working with is I want to give the ionic shorthand for a fluorine ion. I have 10 neutrons, and I have 10 electrons. First off, I'm going to identify fluorine on my periodic table. So I go and I find my letter is letter F. I want to find how many protons I have, my atomic number. In this case, it's 9. Once I have that determined, I want to calculate my mass number. Now I give you neutrons. Refresher, mass number is equal to neutrons plus protons. So I'm going to take 9 plus 10, and I get a 19 for my mass number. Now here's where it becomes a little bit finicky. Now I have my charge. So what I need to do is I need to figure out the overall charge of my fluorine ion. To do this, I'm going to do charge is equal to protons minus electrons. So I'm going to do my 9 minus 10. What's nice about doing it this way is that your negative charge here, is going to carry over. So if you have a greater number of electrons, you're going to have a negative. If you have a greater number of protons, your number is going to be positive. So that way you know, okay, if I have a negative or a positive. In this case, I do 9 minus 10, and I get a negative 1. Now again, you can write that as 1 negative. Both are acceptable. But I have all my parts I need. I have my atomic number, I have my mass number, I have my chemical shorthand, and I have my charge. What I would like you to do now is do the second one on your own. I will go over it in just a moment, but try it on your own. Okay? So starting off, I'm working with the sodium ion. I have 12 neutrons and I have 9 electrons. Just like before, let's identify what we are working with. So in this case, sodium, I have my letters of Na. My atomic number for sodium is the number 11. I'm going to do my mass number. In this case, it's still my neutrons plus my protons, so my 12 plus 11, and I get 23. Again, I'm working with an ion, so I'm given electrons. I'm going to do the same thing as my charge from earlier. I'm going to do protons, in this case 11, minus my electrons. Now this is where that math kind of helps, right? I have my 9 is here, and right away I can tell I have more protons than electrons. So I'm going to have an overall positive charge. I do the math, and I get a positive 2. And that's it. There is my shorthand. I have my charge, I have my protons, mass number, and my element symbol. So I'm good. That is the end of the ionic shorthand along with the atomic shorthand. If you had a difficult time doing this, make sure you try it in your review guide. There are a couple of examples on your unit packet, but you can also use your homework. Also, do not be afraid to rewind past. We are now moving into the average atomic mass calculations. Now, it's important to remember that we're using average atomic mass when we're calculating isotopes. And recall that isotopes are when I have a different number of neutrons. Now, I will give you the mass in like one of two ways. I can give it to you in an atomic shorthand, or I can specify it. Today, we are going to be observing it, where if it's in the top corner. Let's review the reason we solve for average atomic mass. Now recall that average atomic mass is always a weighted average of my different isotopes. Reason why is I'm going to consider that isotope that occurs more frequently or is in a greater abundance in nature. Now the steps to solving average atomic mass are as follows. Your first step is you want to make sure you convert that percent to decimal. All you have to do that is slide 2 spaces to the left. After you do that, you're going to multiply the mass times that converted percent, okay, so that new decimal. And when you are done, you're going to add up all your results. You'll complete this with however many calculations you need to do, whether it's 2 or 3 or 4. No matter what, at the end, you're adding up all 4, 3, 2, however many of the results you have. Let's do a sample calculation together, and then I will give you one to try on your own. First thing is I am going to highlight my percents. So I want to calculate the average atomic mass of chlorine and its abundance in nature if I have 75.77 of 35 and I have 24.23 of 37. Again, my first step is to change percents to decimals. My cat is sniffing my calculator, so let's see if she'll let me use this when we do our math. First, I'm going to start with my 75.77. In this case, I slide my decimal 2 to the left, and I get 0.7577. I do the same thing with my 24.23, and I get 0.2423. Once I have that done, my next step is to multiply my new decimal with that percent. Multiply decimal with, the mass, excuse me. In this case, I want to make sure I'm sticking with the same thing. My 0.7577 would go with my 35. And my 24.23 is going to go with my 37. So in your calculator, you're going to do 0.7577 times 35 and 0.2423 times 37. For my top number, I get 26.5195. For my bottom, I get 8.9651. My last step will be to add these together. So I take 26.5195 plus 8.9651, and I should get 35.4846. If I rounded that up, I would get 35.48. Remember, you can double check your answer by looking at your periodic table, which chlorine is about 35.45. Even though my decimal is a little bit off, I would qualify that as close enough, and I would accept that. Now that we've done one together, I would like you to do one on your own. Here is the one you will do on your own. You're going to calculate the average atomic mass of, spelling error, of oxygen in its abundance in nature, which is 99.76 of oxygen with a mass of 16, 0.04 of oxygen with a mass of 17, and 0.20 of a mass of oxygen at 18. So try this on your own, and I will go over it in a moment. All right, one thing I like to do is just identify. So here is the percent that goes with 16. here is the percent that goes with 17, and here is the percent that goes with 18. Starting with what we know, let's do number 1. I'm going to convert all my percents to a decimal. Again, to do that, I'm just going to slide to the left. So if I look at number 1, I'm going to do 1, 2. I get 0.9976. Doing my next one, in this case, I'm going to have extra zeros. So I get 0.004. Last but not least, 1, 2. 0.0020. Once I have that done, I'm going to multiply my mass with my decimal. Okay, so in this case, I'll do my 0.9976 times my 16. I do 0.004. Ooh, notice that. There we go. 0.004 times my 17. And I'm going to do 0.002 times 18. So I plug these in my calculators for number 1. There we go. I get 15.9616. For number 2, remember I'm going to use my correct amount of zeros. I get 0.0068. And for the last one, I get 0.036. Once I have that done, I'm going to add numbers together. So I'm going to take my 15.9616 plus 0.0068 plus 0.036. I roughly get 16.0044. If I were to round that to 2 decimals, I would get 16.00. If you look on your periodic table, mass of oxygen is like 15.9994 or something like that. 16 would work. So I did all my math correctly. That concludes our calculations with average atomic mass. If this is something that you were struggling with, please make sure that you go back and look at it. But again, there are example questions on your unit packet, or you can look at previous homework. Now we are going to review the history of the atom and our current model. So let's talk about what we know. So the beginning of the history of the atom, we started with Democritus and Dalton. Dalton later kind of went to Democritus and kind of was like, yeah, this is the model we're at. Essentially what both of these dudes thought was that we had small particles that were making us up. However, they did not know about our subatomic particles. So think about it kind of like a marble. There was nothing in it. It was solid, but they're like, we're made of little tiny dots and stuff. And it wasn't until 1987 when Thomson came along that he started doing an experiment that allowed him to discover the electron. He came up with a model, okay, that he pretty much said, you know, the rest of the atom is solid. However, we do have a negative particle that's just kind of around willy-nilly. He didn't know much about it until Rutherford in 1912 did his gold foil experiment, and this is where he kind of was throwing positive alpha particles at an atom to prove Thomson's theory. However, while Rutherford did that, he noticed that 99% of the time, the particles would just go through the electron cloud and, you know, just went through the atom, no problem. But every 1% pretty much, he noticed like, hey, sometimes the atom is coming back. So if I have positive things being thrown at my atom, something has to repel it that's positive. So Rutherford came up that we had a proton and we had a nucleus. However, he did not say it could be in the center. He said we have the electrons going around wherever, and that the proton and the nucleus kind of were just anywhere in the atom. Bohr came out a year later, and this is when he came up with his model. This is the model we primarily use in chemistry. So my Bohr model, where I have my nucleus and my energy levels kind of orbiting the sun. And Bohr is what we kind of existed in. And it wasn't until 1930 that we hit what is called our quantum model. This is essentially saying that the electron can exist anywhere. It's not as nice and easy as our Bohr model orbit, But understanding the quantum model of the atom is what allowed us to really make a lot of transitions into like modern technology. We are able to kind of manipulate parts of the atom that we weren't able to do back in 1913. And so currently we are operating in the quantum cloud model, and this is where we get our electron configuration. This is where in that quantum model that we understand our different orbitals. What you need to really remember is that these orbitals are kind of like our balloons. And it's in these balloons that we can say, here's where the electron is 95% of the time. Now remember, we don't like drawing these. Chemists don't like drawing them. To do it, they have to use a computer model. And the Bohr model is a little bit easier, if not just tedious. So that is when chemists came up with, hey, instead of drawing the images, why don't we figure out a way to write them? And this is where we get our electron configurations. Well, what is an electron configuration? Remember, electron configurations is that shorthand way to represent where our electrons are in our energy levels and our orbitals. So this is where I'm going to use my 1s, my 2s, my 2p, okay? What's important to remember is that I do have a max amount of numbers for each energy level, and to do that, all you need to do is count across. But let's look at the periodic table with electron configurations. So let's talk about the map for electron configurations. So remember, when we're coming up with our electron configurations, we use the periodic table as a map. We're going to use two parts of it. We have our energy levels, and these correspond with our periods or our rows. These are always 1 through 7, and it's from the top to the bottom. And then we have our orbitals, and these are that 3D areas in those energy levels. This is where our electrons are located 95% of the time, and this is our S, P, D, or F blocks. All right? Remember, these are where we kind of get our address. We have our street, and then we have the little blocks that we're in. When you write out that shorthand notation, remember there's 3 parts. You're always going to give me the energy level, you're going to always give me the orbital type, and that number of electrons. Remember the number of electrons, if you're full, you're going to have that max out for your orbital. However, you also can shorten that so that way you can land specifically on an element. Reviewing our road map, this is on that back of your periodic table. You're always going to have your energy levels 1 through 7 from the top to the bottom. You always start with your S block, and remember your S block, you can hold a max of 2 electrons here. Okay, so 2 electrons in my S block. When I get to my P block over here, I can hold a max of 6 electrons, and again, it's just 1, 2, 3, 4, 5, 6, counting along. And my D block, I can hold a max of 10 electrons. We aren't going to worry about the F block. However, you can hold a max of 14. The F block does require a couple set of rules, so we're really going to only operate in our S block, our D block, and our P block. What you really need to know is that order. So remember, it's like reading a book. You're always going to go left to right when you're reading. So you're starting at that first energy level, and you'll just go S block, and then you count over 1, 2 on your way to your location. But let's talk about my specific rules with my S block, my P block, and my D block. So I have 2 kinds of rules that I have to follow when I do my electron configuration. The first one being my Aufbau principle. And remember, Aufbau is that German word for building up. Essentially, I can't just skip to where my element is. The reason why is I need to A, identify how many total electrons there are and where they are at, but B, I can't just fill up where I need to. I always have to start at that first energy level because it's my lowest energy and work my way up. So once I fill up my first energy level, I can go fill up my second energy level, my S block to my P block. I could do my third energy level to my P block. But this is where it gets a little bit finicky. Instead of going to my D block, right, I go to my S block. Okay, so I do 4S, and then I will fill up my 3D. Remember, the reason why is that it takes a lot less energy to fill up my S block with 2 electrons than my D block with 10. So my D orbital is always 1 energy level behind, my F being 2. Just remember that the d orbital is always lagging. Next is Hund's rule. Hund's rule is my box and arrow. And essentially this rule states that if I have more than one box, like my 2p here, I need to fill every box with at least one electron before they're paired up. Remember, this makes sense because my electrons are 2 negatives, so naturally they want to repel. So filling up each box until I fill up and need to do a second is what you need to do with Hund's rule. Well, now that we've already gone kind of over the principles, let's do a sample electron configuration. Starting off strong, we're still going to do number 1 together, and you guys will do number 2 on your own. I'd like you to give me the shorthand electron configuration. Now remember, when I say shorthand electron configuration, I want it entirely written out. I did pick 2 kind of further into it, so that way we reiterate our D block rule. So let's start with silver. So first off, I identify silver on my periodic table. While I do it, I am going to go through from that first energy level. In this case, I start at 1s and I fill it up. I move to 2s and I fill that block up. I move to 2p, I fill this block up. I now move to my third energy level, starting my S block, and I fill it up. Okay. Once I fill that up, I go to my fourth energy level, and this is where my D block rule comes in. I am not going to put 4D. My D block lags 1 behind, so in this case, I do 310, 4P6. Once I have that full, I go to 5S2. And remember, my D block lags 1 behind, so I do 4D, and I count 9 in. This would be my entire electron configuration for silver. Now we've done silver together, why don't you pause the video and try iron on your own? Just like silver, I'm going to start where I began, start from the beginning. So I do 1s2. I go from 1s to the second energy level. In this case, I fill it. I go to the third energy level, and again, I fill that one as well. And just like before, I go to 4s. However, I'm going to be in my D block, and my D lags 1 behind, so I do 3D, and I count however many over. In this case, it is 6. This would be my electron shorthand for iron. Now, I could sit here and say, well, we have our noble gas, or we have our shorthand electron configuration, but there's a way to shorten it, especially when you're working that deep in. In this case, we do our noble gas electron configurations. The first step is you want to determine your target element. So if I was looking at iron, I want to look at where iron is. I want to go back to that previous energy level to wherever it would be full, and I locate that noble gas. Remember, your noble gas is that last element in that last family, my noble gas family. So it's at the end of my P block. I then put that symbol into brackets, and essentially what I'm saying is that I have a full set of energy levels up to a specific point, and I just continue where I left off. So let's do a sample. In this case, let's say I wanted the noble gas configuration for the element titanium. I'm going to look at my periodic table, and I see titanium is in that fourth energy level in the D block. I look at that previous energy level, so the third energy level, and I identify the noble gas. In this case, it's argon, so what I'm going to do is put AR into a bracket, and I'm saying I'm full all the way up to that 3P. Then I just continue like normal. I go to my fourth energy level, I do my 4s2, I have my D block lagging behind, and I fill it up. So in this case, it should be a 2. Pretty easy, and it's better than writing the whole thing out. So what I'd like you to do now is try the second one. Find antimony on there, look at that previous energy level, and find the nearest noble gas and give me the configuration. When I look at antimony, I'm in the 5th energy level, so I look at the 4th. And in this case, my noble gas is krypton. I put that in my brackets. And then I continue on that next level. So 5s2, my 4d, right, lags behind. And I go 5p3. That concludes our noble gas. The last thing we need to go over is the box and arrow configurations. Next is the box and arrow, and this is where we are going to see that rule for Huns, where if I have my P block, I need to fill up all my up arrows before I do any down arrows. So what I recommend doing is writing your shorthand first and then converting those superscripts to boxes and arrows. Let's do a sample. So if I was working with nitrogen, what my first step would be is I'm going to give the shorthand notation for nitrogen. In this case, nitrogen is full at 1s, it is full at 2s, and then to 2p, I am 3 over. So I'm going to draw my boxes. In this case, I have 1s, I have 2s, and remember my p is going to have 3 boxes because I have a total of 6 electrons, and each box can hold 2 total electrons. I start at my 1s. In this case, 1s2 is full, so I give 2 arrows. I go to 2s2, 2s2 is full, so I have 2 arrows, but 2p3 is not full. This is where I need to follow Hund's rule. So I'm going to do 3 up arrows before doing any down arrows. And then I'm done. Why don't you try carbon on your own, and then we will go over it together. Just like before, I'm going to do my configuration. So carbon is full at 1s. At 2s it is full, and at 2p I am 2 in. Just like before, I'm going to give the boxes, and I'm going to make sure that I label them. Okay, and I'm going to do my arrows. 1s2 is full, okay, 2s2 is full, and 2p I have 2, so just like Hund's rule, I'm going to fill all my boxes with up arrows before I do any down arrows, and I get something that looks like that. This concludes our box and arrow method. The last one we have to discuss is atoms versus ions with configurations. So let's go into electron configurations with ions. Right away, we need to recall that an atom versus an ion, there is a difference in the charge. Atoms are naturally neutral. So when I ask for the electron configuration for an atom, your protons are always going to equal your electrons. All right, so if I'm working in sodium, I have 11 electrons and I have 11 protons. I always give the address to nitrogen for this. It is when I'm dealing with an ion that my electrons will vary. Now, what's important to know is that typically ions are always going to match up with a noble gas. Reason being is that if I have a noble gas, that means my energy level is full. Ions are naturally going to be giving away or gaining electrons to have a stable outer shell. And so for sodium, it's easier to give up 1 electron. So I have a full 2p6 shell. What's important to know is that these are always going to match a noble gas. So all you need to do is identify how many electrons you have with the charge, and then find the nearest noble gas and give the electron configuration for the noble gas. Let's try one together. If I have number 1, I want to give the shorthand electron configuration for the following ion. Typically, nitrogen is going to have 7 protons. In this case, I have an overall negative charge, so I know I have to have more electrons. I have 3 more electrons than protons, so in this case, I should have 10 electrons. Looking at my periodic table, I'm going to identify the closest element that has 10 electrons. So in this case, I would have neon. So what I'm going to do for my electron configuration is give it for neon. So this way I can show I have 10 electrons. Neon's electron configuration is 1s2, 2s2, 2p6. And this would be my configuration for a nitrogen -3. Why don't you try Na+1 for me? Just like before, sodium has 11 protons, right? If I have a positive charge, I'm going to have overall more protons than electrons. In this case, I have 1 more proton than electron, so I end up with 10. Again, I'm going to look at what would be my closest element that has 10 electrons naturally, and this would be neon. Again, I give the configuration for the electrons, so in this case, it's 1s2, 2s2, 2p6. That concludes our configuration for ions. Now we are going to discuss light calculations. When we discuss about light calculations, the most important part is that we're really focusing on the electron. Whenever the electron is taking in energy, okay, this is where I am going to jump up. Okay, so in this case, I jump up and I'm going to move into my energy level. So I take energy in and I hop up an energy level. What's important to know is it's kind of like when you have a sugar rush, okay? So I have my sugar rush and I'm going to take all my sugar in and I get a lot of energy and I probably hype up, okay? So I get my sugar and I take my energy in and I hop up. However, I can't live at that place for super long. So no matter where I go, I must come down. And when I lose that energy, I'm going to give off light, okay? Based on the jump, you will see a different color. So if I take energy in, it's absorption. So I take it in, I hop up. When I am done with my energy and I hop back down, I give off light, and this is what I am emitting. Now, based on the jump, you're going to have a different kind of color. If I am talking a low energy jump, so maybe I'm only going from an energy level of 1 to an energy level of 2, I'm going to give off a red light. However, if I have a high energy jump, maybe like I'm going N1 up to N10, okay, this is when I'm going to give off violet or indigo, okay? And it's all about the energy I'm taking in and how far I jump and then when I fall back down. The light that I'm being emitted is typically my visible light, and it will fall in my spectra. You do need to understand how to do calculations with wavelength and using that information to determine frequency or energy. So let's discuss what those calculation equations look like. So in this case, I'm going to have two different equations I'm working with. I'm going to work with my speed of light, which is c. This is a constant, so it's always 3 times 10 to the 8th meters per second. And it's equal to frequency, which is my v, times my wavelength. Frequency is how fast a wave is moving, and wavelength is how big. And when I'm moving into energy, though, my energy is typically an unknown. I have Planck's constant as my h, and that is, again, going to be this number. And my v is frequency. Between these two equations, the things that connect them together are my frequencies. You do not need to know how do I connect these two. However, it could be a bonus question on the test. What you need to know is that frequency allows us to work between the two, and how do you do calculations with wavelength to solve for frequency, or even use frequency to solve for wavelength, or using frequency to solve for energy, or using energy to solve for frequency. But it's also important to know the relationships between my variables. If I'm working with wavelength and frequency in my speed of light calculations, these have an indirect relationship, meaning the higher the frequency, the shorter the wavelength, or the lower the frequency, the longer the wavelength. I use this example in class as if I'm at the College World Series doing the wave. If I'm doing the wave at the College World Series, I might stand up and then I'm going to probably wait for about 30 seconds and I'm going to watch the wave go around the crowd. And then when it finally gets to me, I'm like, oh yes, and I'll stand up and then I get back down. So I'm going to have a long wavelength. I am not at the top of the hill for the while, okay? But it is a low frequency that I'm actually getting up. It's a low energy. Whereas if I were to stand with Mrs. Smith and maybe Mr. Cast and maybe a couple other teachers, and I started doing the wave with them, there's few of us, and so I might do the wave a lot more frequently, and I'm going to be the hump of that wave a lot more. So the longer the wavelength, the lower the frequency. The higher the frequency, the shorter the wavelength. Moving on, energy and frequency, however, have a direct relationship. So if I have a long wavelength, low frequency, that's a low energy, okay? The high frequency is going to have a high energy, and that's my shorter wavelength. So energy and frequency direct. High energy, high frequency. Low energy, low frequency. Frequency and wavelength have an indirect relationship. Long wavelength, low frequency. Short wavelength, high frequency. So I kind of talked about these, but let's do sample calculations. What you really need to know is how do I calculate if I give you wavelength. I'm not going to have you connect the equations. To connect them with frequency, I'm going to do that as a bonus question, but you just need to know the steps for calculating maybe the frequency or the wavelength using the speed of light, or energy or frequency if I give you energy or the other. So let's do number 1 together. What is the frequency of a photon with a wavelength of 434 nanometers? So right away, I'm given to use the 434 nanometers. I want frequency, okay? So the only equation that has wavelength and frequency is my speed of light calculation right here, which I give you the speed of light constant. Your first step is we need to convert our wavelength from nanometers to meters. To do that, 1 meter is equal to 10 to the 9 nanometers. So I'm going to do a train track. So I'm going to use my wavelength, in this case my 434 nanometers, set that in my train track. I want to cross cancel out my nanometer unit. To do that, nanometers will go on the bottom. Meters, where I want to go, goes on the top. Using my conversion, I'll do my 1.0 times 10 to the 9th on the bottom with 1 on the top. And in your calculator, you're going to divide it. This gives me a wavelength of 4.34 times 10 to the negative 7 meters. This is the wavelength I will use in my calculation. So now all I have to do is plug everything in, okay? In this case, I want the frequency, right? So the frequency is my V. So I need to take my equation and rearrange it so that way frequency is on its own. In this case, to do that, I'm going to divide my wavelength over. So I get frequency is equal to the speed of light divided by wavelength. So I will plug in my 3.00 times 10 to the 8th divided by my 4.34 times 10 to the negative 7. The reason it's important that I make sure my units are in meters for wavelength is because I can cancel them out, so I'm left with the correct unit for frequency. So in your calculator, do 3.00 times 10 to the 8th divided by 4.34 times 10 to the negative 7. And I get frequency is equal to 6.91 times 10 to the 14th hertz. And that's it. That is where I finish my equation. So now that I've done one with you, I would like you to try one on your own. So here's your question. What is the frequency of a photon with a wavelength of 645 nanometers? Again, 1 meter is equal to 1.0 times 10 to the positive 9 nanometers. Convert your wavelength and then plug everything in. All right, just like before, I need to convert my wavelength. So I do 645 nanometers, right? 1 meter on the top, 1.0 times 10 to the 9 nanometers on the bottom. I get a wavelength of 6.45 times 10 to the negative 7 meters. I plug that into my equation. Just like the previous one, I am calculating for frequency. So I'm going to divide my wavelength over. So I'm left with frequency is equal to the speed of light divided by wavelength, meaning I have 3.0 times 10 to the 8th meters per second, divided by my wavelength of 6.45 times 10 to the negative 7 in meters. Plug that in my calculator, and I am left with 4.65 times 10 to the 14th hertz. So now that we've had an opportunity to try this with wavelength, I would like us to try one with the energy equation. So let's try this with the energy. So instead, this time I actually give you the frequency, okay? And I want us to calculate energy. So this one, I'm going to use my equation of energy is equal to Planck's constant times frequency. Now I don't have to do any conversions for here. This one's really easy where all I have to do is plug everything in. So I use my 6.63 times 10 to the negative 34 joules times second. And all I have to do is multiply this with my frequency. If I was calculating energy, I would divide it by the Planck's constant, but I do not have to do that. So in this case, I plug everything in and I multiply it, and I would be left with an energy of 3.49 times 10 to the negative 19 joules. This concludes the entire Unit 3 review guide. I know that this was an hour, however, it's jam-packed with information for you. Please use the timestamps in the comments to skip around the video, but I hope this helps you. If you have any further questions, do the ones in your unit review packet, look back on this video, look back on the other videos. But if you have questions, come see me before or after school. Good luck on the test and have a wonderful day. Bye.